Okay, let's go get started here. So last time we were preparing to talk about recurrent neural networks, and I introduced the time delay neural network, which really, let's say the time delay or time delayed neural network, which really introduces a neuronal element that has memory, so that if you've got and if we call the input, I'll call it I, and the output O, then we can define the input and output in terms of time steps. So it's a little bit like a flip-flop or a latch, or so I could say that the output at time k plus 1 is equal to the input at time k, or I could say, actually, I'll say is equal to some function of the input at time k. So you can think of this as an activation function, and you can think of this also as a linear combination of inputs, so weighted combination. And so really the big difference here is that we have this difference in time here. So it allows for sort of memory storage in a neuron. And with such an element, then it allows us to start thinking about analyzing patterns in time. So far, the feed-forward neural networks we've looked at have only been for analyzing static patterns. So I show you a static image, and you tell me there's a flag, there's a face, there's a clock, etc. And things like convolutional neural networks can do that. But if I want to show you things like, I'm going to say, find a particular acoustic waveform. So, like I want to listen for a word. Well, a word evolves over time. Now, there are clever things you can do to make feed-forward networks analyze patterns. So, for example, instead of feeding a convolutional neural network a static image, I can actually feed them a stack of images. And the convolutional neural network doesn't know. I mean, whether it's a stack of images or a single image. And so if I feed it a volume, if I feed it a cube of images, which is kind of like a slice of space-time or something like that, then the CNN can operate on that whole cube simultaneously. But by doing so, I'm effectively increasing the memory in the system, because now every input to the CNN has got to be this giant volume of history of these last slices. And so this is another way that we can think about doing that, where we're putting the memory inside the network and not kind of inside the input. And so I gave kind of a simple example where if I've got an input, say X, and it goes into some, I'll say H1, which goes into an H2, which goes into an H3, and that is my output coming out of H3. And if that, I think in my example, I think I just passed X directly to H3 as well. Make sure I'm consistent, or I patched H1 to H, or I didn't call this one H3 here, but so I patched H1 to H3. And I said that the activations of functions are set up so that if this is y of k, then we can call this like H3 of k. But H3 of k is going to be the delayed version, it's going to pass version of whatever H2 of k minus 1 is. That's what this line is here. And then H2 of k is going to be equal to whatever h1 of k minus 1 previously was, and h1 of k is going to be equal to whatever x of k minus 1 previously was. And so if I extend each one of these, if I then kind of go forward here, then I see that this middle node is actually x k minus 2. And so at h3, it allows for comparing x of k minus 1 and x of k minus 2. Because this line here is also x k minus 1, because it's just a copy of that output. And so that allows me to look for patterns here that are in 2 time slots. And so I could set up an activation function on this output here, which only activates when certain things are true about these things. So when they're both equal, when the average of these things is both above a certain value, and so on and so forth. And by setting up a function of these past versions of the input, it allows me to look for patterns in time. But this purely feed forward topology that we have here has the downside that the longer patterns that I want to look for in time, then the longer the network I need, because every new element, every gap basically is a bit of history that I'm storing. It's a slice of history that I'm storing. So if I need to look for a pattern that evolves over 12 time steps, I'm going to need 12 gaps for me to store this delayed version where I've got maybe the beginning of the pattern and the end of the pattern, and they're separated by 12 gaps in between them. So that's the upside to these feed forward networks, or these so-called finite impulse response systems, if they're all linear, is that they're pretty easy to analyze, and the patterns they don't have any sort of weird side effects that I'll kind of mention in a second for the alternative case. But the downside is they can take a big footprint in order to look for a big pattern evolving over time. So instead, what we can do is add recurrency. And so if I have my x here, and I run it into, I'll just say a single, I'll just call it h1 for kicks here, and it produces a y, but I also run the output back into the input, then this means that yk is going to be a function of x k minus 1 and the previous y k minus 1. So by setting up the activation function and the thresholds and whatever else on this neuron here, then now I can look for patterns that are related to my input and my past output. And so my output is something I have a little bit of control over. So the neuron itself is sort of a persistent mark that the input leaves on the network. So now, if something were to happen in the long past that causes the output to change, then now I don't need to remember when it happened in the past. I just know that it happened in the past. And that then can be used when I'm processing new inputs. So recurrency, being able to pass neurons back to either themselves or to neurons that are sort of upstream of them so that they eventually come back to themselves, allows us to search for patterns that are much sort of wider in time with using fewer neurons. The downside of that is these feedbacks introduce dynamics into the neural network, which can create interesting things where, like, you might have an input, but your output will keep changing. So it's kind of like, if I have a glass bottle and I hit the glass bottle and it rings a little bit, and it kind of rings sort of forever. And in part, it's because the structure of the glass is feeding back on the future oscillations of that glass, and so there's memory in the glass, and that that ringing eventually damps out. But if I have a kind of a more complicated system where things are reinforcing each other, sort of like if you were to build a little robot that whenever it heard a tone that was certain, that it was loud enough, it had actually ended up striking the glass again to keep it ringing. Well, you might think that you're doing a right thing, to sort of keeping memory in the system by this robot constantly ringing this glass, but you might not anticipate all of the interesting patterns that can come out of this system, like weird things that robot can do if it doesn't hear things quite right. You might get weird oscillations and things like that. And that's what happens with a lot of these recurrent neural networks, is that the outputs can be sort of an unpredictable from the inputs if you're not careful on how to design them. But so this is what I'm going to call a basic recurrent neural network. And so in general, though, I mean, they can be useful. And so imagine that multi-layer perceptron that we had before that was all feed forward, and now allow for arbitrary connections from any neuron to any other neuron, so long as there is a time delay neuron somewhere in between them. So they all could be time delay neurons, or they all could be kind of your regular sort of instantaneous action neurons, but there has to be at least one of these that sort of separates before from after, and that's what allows for that feedback. And so you can imagine very complicated networks like that. And so I could draw kind of like a generic RNN topology, and so the generic RNN is a mess. It's a rat's nest where you'd have, all your inputs, fine, my input layer, great. But then all of those, so those end up going into, that first layer. But then at that point, I might draw these as layers, but really it's hard to separate them into layers at this point, because, any one of these could go here, could go back here, these could go back here. There could be all sorts of feedbacks that make it difficult to figure out what the right sequencing is going on here. So it's just kind of, effectively arbitrary connections. Between latent variables. And so a lot of times, instead of drawing things out like this, we just skip to kind of the matrix interpretation or the functional interpretation, which is what you end up doing when you're programming neural networks anyway. And so you could just refer to sort of this as your feature vector X. And then this ugliness inside here, we might refer to as another vector H, which is a hidden state. So before, the hidden variables, the latent variables, were all immediate functions of the input. They were just filtered versions of the input. But now, because we have these time delay neurons, then you can have neurons that their history matters. So like if I go back to this simple RNN here, whether the output is on or not depends on whether an input met a particular condition way in the past. So now I need to keep track of the state right now. What is the current state of the output? I need to know that. So likewise, in all of these, whenever I have one of these time delay neurons, inside these hidden layers, I really have a hidden state, which is what is the state of all of these current neurons. And so that state evolves. And so I can write an evolution where I can say that part of the evolution is going to be some matrix operating. I guess I should separate these in time. So the next value of the hidden state is going to be some matrix times the current value of the hidden state in part, but then it's also going to be a function of the input. So those of you who've taken a systems theory class or a controls class, this should start looking maybe familiar to you. It's the same sort of idea in state variable models for dynamical systems. The hidden state are the state variables for this system that we've created, and they evolve based on feedbacks from their current state as well as forcing functions from the input. And so then the output similarly can be broken up where we say the next output is equal to some matrix transformation of the input here. And depending on how I wire up the output, it might be separated by a time delay or not. And in theory, you could actually add a feed forward term that is directly dependent upon the input. So plus dxk, that would be fine too. But this is kind of the simplest thing here. So this ends up being a more convenient way to write recurrent neural networks where the weights are stored. We can think of these as hidden layer weights. And you can kind of think of these sort of as, I don't want to call it input layer because they could go deep into there, but that's kind of, I'm going to write that, but that's not exactly what I mean. So I'll just say input weights. And you can think of this, again, I don't want to call it an output layer because things aren't, they don't fit into these nice slices anymore, but I'll call these output weights. And so training your recurrent neural network, and we'll talk about how to do that, is just training the weights in these matrices. All right, so yeah, so any questions about, so I guess if you wanted, I could draw this symbolically. As I could say, I've got my input vector. It goes into this hidden state, which produces some output via the C transformation, but then the next hidden state depends upon the input vector as well as past versions. So that's kind of a graphical depiction of our hidden, of our recurrent neural network, something along those lines. A generic recurrent neural network. Okay. So any questions about this basic structure here? All right, so one thing is that, well, how do we train this thing? Well, we learned that backpropagation worked really well for feed-forward neural networks. And it turns out you can also train these recurrent neural networks with something called backpropagation through time. And I'm focusing on this kind of diagram here. So we can train RNNs with, of course, you could use other methods. You could try genetic algorithms, all sorts of optimization meta-heuristics we've talked about. But one common method is backpropagation. I'll just abbreviate that, through time, right? Through the kind of silly American way, or BPTT, backpropagation through time. And what backpropagation through time does is it's an abstraction that unrolls the execution of the recurrent neural network for a certain number of time steps, and then treats that like a feed-forward network where all the gradients get added together. So I don't want to get into too much detail about this, But I just want to give you kind of a sense that simple backpropagation methods can also be used with recurrent neural networks, even as ugly as the combinations are. And the way we kind of view it is, you could imagine that if we want to unfold a network in time, then we're going to have these nodes. These are those hidden states. And I might have my hidden state at time k minus 1. And I've got my hidden state at time k. And I've got my hidden state at time k plus 1. And so you choose some time window that you'd like to kind of unroll. And we know that the hidden state in future time depends on the past time, and so on and so forth. And so we can write that dependency as pretending like it's kind of a feed forward relationship where there's this matrix A, which helps to translate the past hidden state to the next hidden state. And then we've got our x vector coming in from time k minus 1, and we've got our y vector at time k, and we've got our x vector at time k, our y vector at k plus 1. Here we've got our x vector at time k plus 1, and our y vector, or our y output at time k plus 2. And so by unrolling this, so this is an abstraction. So by viewing the recurrent neural network in these time steps, we now can, you might have to unroll it for a finite window or something like that to approximate this, and hopefully that's long enough to be useful for your training data. But now you can view this structure as a big feed forward neural network, where it's the neurons, the weights here are viewed as sort of being independent from the weights here, as viewed as being independent of the weights here. But then you end up adding all the gradients together. So this ends up being training data for this sort of induced neural network. These are all the inputs. So these are all the inputs down here. These are all the outputs here. And so you can end up kind of using this backpropagation. You can sort of view this as a kind of feed forward representation of an RNN, and then train with an analog of backpropagation. And then where you're going to then add gradients together. So in other words, if you do this backpropagation thing, you're going to sort of be, you're going to calculate gradients for weights in one network, and then you'll end up calculating gradients for those same weights in another network as if they're independent from this other one, and so on and so forth. And you'll end up doing, as you'll go back through and calculate all your gradients, then you add all the gradients up together for those weights, and that's how you take your step. So it's just a way to sort of decompose the execution of a recurrent neural network into this approximation where we view it as a feed-forward network and then use backpropagation on it. So that is a traditional way to train recurrent neural networks. And Gesundheit, and as we'll see, I see there's a question online, as we'll see, just like a multi-layer perceptron is very difficult to train, but a convolutional neural network is easy, there are similar regularizations that we see with recurrent neural networks, and I'll introduce one of them briefly, that make training much easier. So backpropagation through time works in principle, but it really, in practice, you have to kind of have a nicer recurrent neural network for it to work very well. And we'll define one example of a nicer neural network that's been very successful. All right, so there's a question online. does backprop flow from A backwards? Backpropagation through time, view it as flowing. So I'm glossing over some of the details here for how the errors enter, but it's you can basically consider it being rolled backwards, where these are sort of the outputs, these are kind of like the output layer, and this is sort of moving in this direction. So I know that it's a little weird because I've got the inputs coming in here and the outputs coming in here, but I'm saying it's back propagation this direction. But again, I'm glossing over some of the details on how this works. But the whole idea here is you're just creating a feed forward approximation that's going to duplicate weights, but that's okay because you're going to add all those gradients together. So if you're interested more in backpropagation through time, you can find a more detailed description of how it works. I don't really want to get into that because it just gets into the weeds, and you can imagine it was bad enough writing out all of the expressions for just normal backprop. So it gets a little uglier when you're talking about unrolling these things, but you can certainly look up BPTT to find those details. But I'm basically just want you to have exposure that there does exist a backpropagation analog for recurrent neural networks, and it can be applied pretty much just as easily as backpropagation for feed-forward neural networks, and it's called BPTT, backpropagation through time. Okay, any other questions with this basic idea? So we can build neural networks, we can train neural networks, but not all recurrent neural networks are as trainable. And so just like we had the convolutional neural network being kind of the regularized or lower complexity version of the multilayer perceptron. Yeah, question? Well, so this vanishing gradient problem, that's what I'm kind of talking about now, is that when you have a very complex neural network, then you can have these vanishing gradient effects. And the way we get rid of those is by regularizing the network. That's one of the reasons why we get rid of it, to sort of make the network simpler in some ways, maybe so there's less weights, maybe it's not as deep. And that's what we did when we went from a generic multi-layer perceptron to a CNN. A CNN had fewer weights to worry about, and so it had the negative aspects of gradient descent didn't apply as much. And that's the same thing as what we're about to do here. And so a popular, or I say popular and good performing RNN is what's called long short-term memory. Which is usually called LSTM. And up until, so I'll mention an aside, and I'm not going to write a lot here. I'll just say C transformers. And this is particularly for natural language processing. So, the topic of transformers is a little bit outside of the scope of this class. I don't really have anything prepared that I can speak intelligently in front of a class on it, but I do want to at least mention that for a long time, LSTM was the go-to tool for text prediction, for example, for a lot of applications in natural language processing of trying to analyze, and predict what needs to come next. And but as of more recent times, these so-called transformers have taken over, which are actually feed-forward neural networks. So if you might have heard of things like GPT-3, for example, that's one that's very popular. And there's a bunch of others now. So what I'm going to say, I'll give kind of an example, like a text search example, but it's going to become more and more dated because gradually everybody doing these sorts of things is switching over to using transformers. So if you really want to be on the bleeding edge of this stuff, then I recommend you look up information about these so-called transformers and how they work, which are sort of some simpler structures, but they're trained on massive amounts of data, which makes them so amazing at what they do. But I'm not going to talk a lot about that. I just want to mention it there. I just want to make sure it gets a little bit of airtime. So what LSTM is a type of recurrent neural network that breaks, it separates out, it simplifies the generic recurrent neural network so that there's kind of compartments that, so not everything doesn't connect to everything, but it's kind of broken up in sort of an intelligent way. So in particular, the LSTM, it breaks the hidden state, which, H, which you can again think of as memory inside the network. It breaks that up to, I'll say breaks up hidden state to include a special cell, which I guess I'll name, but I'm not going to write out a whole lot of the details of this, that stores values for long durations of time. And this special cell in the hidden state can be, there's neurons will enable and disable access to it. So it can be gated so that you can write to it. It can be gated so that it can be read from. So there are these gates that, so based on the current, text maybe that's coming through in a text example, I'll give you a text example in a second. It will say, do I need to combine this input with information from this memory that is very long-lived? Do I need to update this long-lived memory based on my input text, or do I leave it alone and not process this at all? So there will, and I'll give an example of this in a second. I'll make this clear. So I'm just going to write this down so I can get it down here, so that it includes gate units that control access to this cell, and I say read, write access. All right, so what the hell am I talking about? So the idea is, let's say, for example, someone types into your favorite search engine something like, or types into, let's say you're using Google Docs or Microsoft Word or whatever, and you're writing along, and they want to help you, and they want to help predict what the next word that you want to write is. And you write somewhere in the middle of your document, the boy called thee. Hold on a second, wait for my pencil to come back. There it goes. You write, the boy called thee. And then the question is, what comes next? Now, without, you could say, if I could take the max entropy approach and whatever, and I could say, every time anyone's written the boy called thee, what's the distribution of possible things that could come after that? And I could kind of make the best prediction based on that. But I have a lot more context because I have the rest of the document. So it's looking down at the rest of the document, and it can remember from the rest of the document earlier things that were written about what was going on with the boy in this story. So, for example, let's say that earlier in the story, there were cues that said that there was a fire. So earlier, I'll say, earlier we see fire. So then that would predict that maybe this word should be fire station, or this should be completed fire station. But then maybe instead, it's earlier. We see that there was some sort of contextual cues that weren't related to fire. They were related to, I don't know, happy feelings or something like that. So then that might mean that its prediction is not that he called the fire station. He might have called the cell phone of his girlfriend. So so this here, this earlier thing, this is stored inside that cell. So basically, as it's learning, as it's going over this text, earlier it's been trained that to keep track of certain things. So it knows, so in previous training, the LSTM has learned that based on human text, when you're going through here, there's certain cues that should cause it to update the internal memory in this long short-term memory cell. And that, and other cues should just leave it alone. So it knows that maybe when there's certain types of words like fire and happiness that cause it to update this internal representation, this internal memory representation cell, and then downstream when it needs to make predictions, the predictions are based not only on words nearby, but also on this state that has been hanging around for a long period of time. And this allows it to make more intelligent predictions that are that match to patterns throughout the document, not just local to the word that's being predicted here. So that's kind of the insight. When long short-term memory was built, they said we're going to effectively not think about these neural networks as neural networks. We're going to think of them as memory, and we're going to keep track of a coarse-grained state that sometimes gets updated, but very often is left alone. It gets updated very infrequently, but we can read from it to change how we predict things based on short-term things that we keep track of as well. So it's long short-term memory. It's short-term because it's working memory. It gets flushed out periodically. So it'll go from fire to happiness, back to fire to something else. But it's long short-term memory because it might not change in a whole paragraph or in a whole chapter. It might be, it might not get updated because it doesn't get triggers that we've changed our context. So that's an example of how you can kind of regularize these recurrent neural networks. It just means how do you structure them in an intelligent way so that there's fewer weights to worry about, so that when you do things like backpropagation through time, it's a little less complex of a task. And if you can make the task less, neural networks are all about this regularization thing. Like sometimes it's depressing. You'll train a neural network and you'll get certain performance, and then you won't change the neural network at all, but you'll play with the optimizer. So you'll change the step size in the optimizer, or you'll add a little bit more noise if it's got stochasticity in the optimizer. And you get a totally different performance out of your neural network. That's because it's hard to train neural networks. So whatever you can do to make it easier to train neural networks will make for better performing neural networks. So in theory, recurrent neural networks, you just throw all the recurrent connections in and it'll magically figure everything out. In reality, our optimization algorithms are not that good. And so what we want to do is want to make it easier on the optimization algorithm. So we do that by simplifying the networks. And that's all LSTM is it simplifies a recurrent neural network so that it doesn't have to use that much memory, but it uses memory in a very intelligent way, keeping this long short-term memory. All right, so I don't want to go into too many details about LSTM, but I just wanted to give you an idea, just like going from MLP to CNN, how you can go from RNN to LSTM to make the things simpler. So any questions about that? It's a good technology to know about, LSTM, just because it's still very widespread. Okay. All right, any questions online? Let me make sure that's not a question online. I think, okay, good. All right, so the last thing I want to talk about in our supervised learning section here is also another recurrent neural network that I want you to be familiar with. And so this is RNN example 2, where it takes regularization to a very different place. And this is our echo state network. Otherwise known, which is kind of that's sort of like the trademark name, I guess you could say, but more generically, these type of networks are called reservoir machines. So you should remember both of those because they're popular names, echo state networks or reservoir machines. All right, so what are these things? So here, what they've said is it's a pain to train all of these recurrent neural networks, but maybe there's a way to capitalize on their memory without having to train them. So what they do, what this is, the idea that this is inspired by is, imagine if you had a cup of water. How many people have seen Jurassic Park? I know it's a small room here. You know, the original one with Jeff Goldblum and all that. Do you remember the scene where there's like a cup of water on the dashboard and the Tyrannosaurus Rex is coming near, and as it stomps, it has ripples across the water? That's the picture I want you to have right now. So you have a cup of water with that water is on top of here. And it's sitting on a table, and some input bumps the table. So there's a bump of the table, bump. And that creates vibrations across this water. So there's vibrations from the bump. All right, now in theory, you can actually, like, what's cool about what happens here is that bump happened once, bump, but it left an imprint over time here. And if you had multiple bumps, then those imprints would kind of combine together and it would set up a pattern in the water. So if you bumped this table in different ways, you would get different patterns across the water. So the thought is that you can take temporal data, so time series, and then turn it into spatiotemporal data. So you take something that's just changing in time and you suddenly project it into a space where different points in space are changing in time in different ways. And they're all changing because of this original input. So you're projecting something that's just changing in time to changing in time and space. And the thought is that maybe this filtering of the input, this sort of, you actually can use the ripples on the top of the reservoir. So this is this cup of water. So the cup of water is a reservoir. And you can use the ripples that are spreading out on the cup of water as an information source to tell you something about the temporal series. So that, in effect, those vibrations have memory of what's happened in the past. Because, as I bump that thing, those vibrations last much longer than the bump. So if I bump it multiple times and those vibrations interact, then really what we're seeing is mathematical operations being applied from present versions of the input to past versions of the input, and you're getting some pattern that's out of there. So you can imagine that maybe you could aim a laser vibrometer at water to generate features across the surface. And then train a single hidden layer network based on them. So this is the basic idea behind an echo state machine. So if I were to, and I'll draw, make this a little more specific to neural networks in just a second, but the idea here is I have an input. This is like whatever my X input is, which may change over time. So I'm looking for patterns over time. It then gets filtered or spatiotemporal projection. And then that single input in time generates a feature vector, which then that feature vector can connect to a single hidden layer network, which then produces an output. And so now I can put in time series, like, whether is this a certain note, is this a C note or a D note or whatever, and I can build classifiers for that. And all I have to train is this. So train that right there. So we know how to train single hidden layer networks. You can do that with gradient descent, or you can do that just with like pseudo inverses, like least squares methods. So this training task is pretty easy. So how the heck do we generate this spatiotemporal projection? Well, that's where the recurrent neural networks come into play. And I see there's a question online. And so, so the idea here is you can create a random recurrent neural network. So the idea is you've got your inputs coming in, and you just define a certain number of nodes inside here, and they're all connected to each other in random ways. So you say, I want 500 nodes, 500 time delay neural network neurons inside my recurrent neural network. I'm going to randomly define their weights. So I'm going to randomly draw who's connected to who and how many connections are there and things like that, so that I just get this random transformation of this output. And then each one of these neurons, each one of these hidden, these variables in the hidden vector can itself be a feature that can be inputs to your single hidden layer network. And so, so you can take these as outputs, maybe some of them or maybe all of them, and then these here become the kind of X feature vector for the single hidden layer network, which produces that output. So random recurrent neural networks are basically, it's a random dynamical system. So the potential beauty of this method is if these are truly random, then there shouldn't be any bias in how they stretch out your input signal, but they will stretch it out over time. And by turning temporal patterns into spatial patterns, then I don't need any memory, any recurrency in the actual network that I need to train. So again, I'll emphasize only train this feed forward network. And it is pretty simple to train this feed forward network. So spreading this, spreads time into space so that feed forward network can be used. So that's the insight there with these reservoir machines, is that if really all random recurrent neural networks are doing is sort of keeping track of data over time and then assembling outputs based on on inputs from past time, then maybe we can actually do pretty good just generating a random latent space, a random latent state vector that if it's kind of chaotic enough, then it will have its own sort of interesting characteristics that it'll find, and we can queue off of those, scale them in certain ways, and then we just have to train these few weights. So there could be a lot of weights in here, a lot of interconnections, and we just don't care about them. We just draw them totally randomly, and we bolt on a relatively simple decoder. So we could call this, basically as a decoder network. And so these echo state machines, reservoir machines, are great for things like time series classification, time series analysis, because they do tend to cut up these variables pretty well, and they're very sort of economical to train because you only have to train a certain number of weights. I saw there was a question online from a bit ago here. So the question is, do we look at one frame of the spatiotemporal data or a window of the spatiotemporal pattern? The answer is things aren't cut up into frames in reservoir machines. The idea here is that we don't know kind of the decay, we don't kind of know the time constant of this system. These random connections, you could hit the input with a spike and this thing could ring for a huge amount of time. So when you're looking at here is you're just looking at snapshots of the internal state of this dynamical system. And so they're spread out over space, but each node, it's like some nodes are going to be more influenced by recent inputs. Some nodes are going to be more influenced by farther out inputs. So there could be some nodes in here that effectively memorize really long time ago periods, and other nodes that forget very quickly. And so it's not like this isn't a buffer that's storing data. This is it's a plastic deformation in this dynamical system. Well, I'm going to say it's an elastic deformation in this dynamical system. In theory, if you let your input go to zero, eventually all this would die out. But we actually don't know for sure that this system is stable. And so it might be that you set your input to zero and this thing keeps ringing along, and that might be a bad feature. So if you look up in the literature on echo state networks, they have guidance on how to actually draw these random weights so that you get the best performing echo state network. But the important thing here is you don't train any of these weights. They're totally random. You only train the decoder. And the decoder is just a plain old vanilla single layer feed forward neural network. All right, see there's another question online. So there's a question, so I haven't talked about unsupervised learning yet, but there's a question that said, is this an example of unsupervised learning? No, this is supervised learning, because we have, we train, this is, input from training set. And this output is also from training set. So this is plain old supervised learning. We're still in the supervised learning domain. The reservoir network doesn't figure out what it needs to learn on its own. And we haven't talked about unsupervised learning, but we're about to next time. But it still is doing plain old, here is an input, a signal that I want, like, this is a C note. I want you to classify this as C. This is an A note. I want you to classify this as A. And so on and so forth. You train this thing, but you don't train it based off of static things. You train it based on time patterns. Here is, here is a stock. Here's a pattern of stocks, trading on the markets. Here's a pattern of stocks that happen just before a rise in the market. Here's a pattern of stocks that happen just before a fall in the market. And so if you train from enough of those, then perhaps this thing will be able to predict whether the market is going to go up or go down. But it's all supervised learning. You have to provide it training here, and then you train this during the training portion. And then once you're done training, you do your test and validation, and I'll mention that here in a second. But then after that, you turn off the training and you let the thing run, just like any supervised learning, just like any other neural networks we've talked about so far. So it is still supervised learning. You just have this weird filter in between. All right, and the other question that was online here is, so we look at one snapshot, and that snapshot's fed to the feed-forward neural network. Okay, you're looking at a snapshot not of the input, you're looking at a snapshot of this reservoir in between here. So it's like looking at a snapshot of the ripples on the top of the glass as the Tyrannosaurus is coming in. Imagine if you wanted to classify what dinosaur was coming up by looking at the ripples on that glass. And so your feed-forward neural network could look at one snapshot of the ripples at the top of the glass and say, that's a Tyrannosaurus, that's a Velociraptor, et cetera, et cetera. And so that's kind of what we're doing here. We take a snapshot of the hidden variables, of the latent variables, not a snapshot of the input. And the hidden variable snapshot will capture multiple time scales of the input. All right, so any other questions about reservoir machines, echo state networks? And this, I would argue, is another sort of approach at regularization of recurrent neural networks, because you get a lot of the same benefits that you get out of a recurrent neural network, but the training is super simple. So it's not as over-parameterized as it would be if you had to train all of these weights. You only have to train these weights. Okay. All right, so the question came up recently, supervised learning. So I did want to at least take an aside, because we didn't really talk about this when we were talking about our optimization meta-heuristics, but we probably could have. And so when we do supervised learning on neural networks, you're going to see people talk about 3 data sets that they use. They have their training set. So they have training data, they have validation data, and then finally test data. And so basically the training data, it's kind of 3 different scales of test. So this here is what actually updates neural network weights. The validation data is actually what helps you choose better hyperparameters. So this is like number of nodes. This is like optimization, optimizer parameters, etc. And then this is actually, the real evaluation. So basically, if somebody gives you a boatload of data that has a bunch of known inputs and desired outputs, you cut that data up and you put a little bit into training, and then you have data that was not used into training, and you can use it for validation. And you see, because the thing is, if you give, neural networks are over parameterized, which means there's so many weights that you can get like a near 100% accuracy fit on whatever data you use to train, just because you can effectively encode the data set. So with your training data, you might get 100% accuracy or so on, but then when you're going to try to run your network, not train it, but see how well it does on a small data set that it hasn't seen before, and you're going to see that, oh, actually, it's got like 50%. And you're saying, well, that's not very good. So that might mean that my optimizer effectively loaded up all of these training data into my network, and I can't generalize beyond this training data. So I need to fix my optimizer so that it's better regularized. Or I need to change the number of nodes. Maybe I have too many nodes, and so on. So if you don't do well in validation, you can go back and either update your neural network or your optimizer and retrain, and then try this again. And then if you eventually get to the point where you're very good on your validation data, then you've got another slice of your data set that they've given you that you haven't used yet that you can actually do your test. And that's going to be totally independent from all these. And if you come out and you've got like 95% accuracy on your test data, then you've got maybe a good signal that you've actually got something that can generalize to other data that hasn't been seen before, because it hasn't ever been trained or validated on these data here. So we usually split data up. So split up data. And I could have suggested doing this with your optimization meta-heuristics as well. We have a bunch of hyperparameters. So you could imagine when you're doing your optimizations, you can give a little bit of, you can do kind of some test runs with certain hyperparameters, and then you update the hyperparameters, and you kind of update the test runs, and so on and so forth. So optimization is not necessarily always supervised learning, but we could still kind of envision the process of updating your optimizer in these type of 3 steps, where you kind of use like a small number of generations to see how well it does, update the hyperparameters, small number of generations. As things do better and better, with small numbers of generations, you eventually fix your hyperparameters so you're done. You know how many individuals you want, you know how many generations you want, and whatever. And then you actually go and run the large experiment that takes a huge amount of time, but you feel pretty confident that your optimizer is going to perform well. So this is effectively, this idea of cutting things up into 3s is really common in data science and optimization. So, and that's sort of, you'll often see these words, training, validation, and test, and that's where this comes from. So any questions about this concept of breaking your data up into 3s like this? It's something that some of you have probably already done before in some other projects and other classes, but just wanted to make sure that I captured that. Okay, so where are we going next? Okay, so basically what I'll mention here a little bit for the last couple of minutes we have here, and then what we'll pick up on next time. So we're a little behind schedule for this, but I think we can catch up. So we've been talking about supervised learning, and that is one type of learning. There's already been some questions in the chat about unsupervised learning, and that's one of the things we're going to talk about next time. And so, basically, so far we've talked about supervised learning, which is all offline. So we have offline methods. So offline supervised learning. And the key features here is that we have ground truth data, and we provide rewards for accurate outcomes, for accurate inferences during training. And that's what supervised learning is. Now, there are forms of online learning. And so the reinforcement learning is an example of this. And in reinforcement learning, this is typically deployed on an agent that interacts with its environment, or it has to update its learning parameters in real time. So it's easy to think about a robot moving around a space, doesn't know how to navigate that space, but this could just as equally be some advice agent that has to learn how to give advice the more people come up to it. And so based on their feedback on how well the advice was given, then they can can learn as we go. And so reinforcement learning is, generically speaking or abstractly speaking, a method for exploring an environment and discovering actions that maximize rewards, or I'll say accumulated rewards. And so if you're familiar with Markov decision processes, this is very closely related. So in a Markov decision process, you take an action which changes the state of the world, maybe your state, maybe the world state, and maybe leads to a particular reward. And based on that reward, you take another action. And so you can model reinforcement learning with a Markov decision process. And there are related concepts like partially observable Markov decision processes, which relate to how much information you're getting back from the environment about what state the environment's actually in. So we'll go into more detail of that on next time, but that's sort of one, so that's the idea of online learning with rewards. But then there's also unsupervised learning. So in unsupervised learning, there are no rewards, no given rewards. And so here, the neural network sort of rewards itself, and it does that by actually finding patterns. And so we'll see examples of this next time, but the basic idea here is if you give a neural network inputs that, a variety of inputs that have features that always seem to light up the same way, then that neural network is going to learn over time that those features that are connected in some special way, and that when those connections happen, that's maybe one special group. And so it learns to recognize things like, oh, I noticed that yellow always goes with red. I noticed that orange always goes with blue. And it starts to create abstract concepts out of these associations that it recognizes. And so unsupervised learning is when you have a data set and you have no idea what's there, you run the data set into the neural network, let it chew on it for a while, and then you start noticing that the neural network starts slicing up that data set into slices that maybe you didn't think about, but afterwards, by looking at them, you see, oh, I see. These are all the people who eat cookies, and these are all the people who drink milk or whatever. And so it ends up sort of finding the relevant features that might be useful to you for other sort of studies. And that's what we'll kind of get into next time. So that's, and then I'm going to also talk a little bit about associative learning, but these are sort of the three major categories here, where we've got supervised learning, reinforcement learning, and unsupervised learning. And they all differ kind of in how they're executed, online or offline, and whether rewards are provided. So, and in all of these cases, there are neural network frameworks that can be used to facilitate these types of learning. But these types of learning go much farther back than neural networks. These are kind of in the kind of good old-fashioned AI machine learning days. There are plenty of other mechanisms that also can be used for these three things, but it just so happens that neural networks do a pretty good job at these things too. So that's where I'll stop. That's where we're going next time. If you have any questions, feel free to come up afterwards. Otherwise, have a good weekend. Don't forget there's a muddiest point. I think also your proposals are due. Remember the short proposal with your group about what you're planning on doing so I can review those. Maybe they're not. If I might be correct, maybe it's next weekend. Sorry, but double check that. I forget if it's this weekend or next weekend. I didn't check before class. I'm sorry about that, but double check that. Definitely a muddiest point is due though. And I guess that's all I got. So have a good weekend. Go ahead. Oh, and let me go ahead and 1, 2. All right, so online, I've got a question here, so I'm going to go ahead and stop the recording, and I will go ahead and mute my audio, but I'll hang on. If anybody's got a question online, then I'll come back once I'm done here and see if anybody's still hanging around.